Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Fall slowly, and you try it more. Most wonderful good afternoon. Most wonderful good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Most whatever. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Not the first today. Good afternoon.
I had to go down to town.
Oh, you are slacking, eh? Most wonderful good afternoon. Most wonderful good afternoon. Good afternoon. Most wonderful one. Good afternoon. Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Good after, most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Most wonderful good afternoon.
Sometimes you get an answer, sometimes you don't.
That's absolutely fine. That's absolutely fine.
Something's gone wrong along the way.
Well, maybe they haven't arrived on that planet yet. Or, deep in thought. Most wonderful good afternoon.
My asthma's really bad today, so if I cough, I apologise.
Well, as long as you don't start.
I've got my inhaler.
Oh, good. A very good afternoon. Most wonderful good afternoon. You can do a sort of a survey. Most wonderful good afternoon. Hi. Good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon, everybody. Good afternoon.
Some of you just they grin at you and think, oh, what's going on?
Oh, it's Friday afternoon. What do you expect? Yeah. Most wonderful good afternoon.
Good afternoon.
What is it?
Statistics for my poor bioscientists. Most wonderful good afternoon. Sorry? Yeah, I told them on the group chat this morning what's the topic of this lecture, and the comment was, God help us. I told them they don't have to call me God. Peter is fine. Peter is fine.
Not English though, are you?
No, I'm from Germany.
I thought so, that's why it was wonderful good afternoon. Wunderschönen Nachmittag. Wunderschönen guten Nachmittag.
Genau dasselbe.
Ja. Well, I thought, what a beautiful
Ja.
Ich habe in Hannover 28 Jahre gelebt. Ich bin Engländerin, aber noch da 28 Jahre gelebt.
25 years here.
Yeah.
That's for me.
Yeah, it's the other way around, yeah.
Hanover doesn't have any accent.
Where do you come from?
Bavaria, the south. Deep south.
Deep South.
Mind you, I've lived 4 years in Göttingen,
Okay.
and it was quite interesting because most wonderful good afternoon, Alex.
To you too.
Thank you. Because in Munich they said you speak absolutely accent-free German. We wouldn't know that you are from Bavaria. That was in Munich, right? In Göttingen they said good afternoon. In Göttingen they said we can't understand you. It's such a thick Bavarian accent. Good afternoon. Good afternoon. Can't win.
Can't win. Very
Absolutely, I have problems. Good afternoon. Okay, yeah. Good, most wonderful good afternoon. Ah. Yeah. Again, it's very distinct. Oh gosh.
So they'd gone from Hamburg down to the south, and
Good afternoon. I can see that there are some initial communication issues. Most wonderful good afternoon. Most wonderful good afternoon. Oh dear. Good afternoon. Good afternoon. Very good afternoon to you.
Let's go.
Let's go. Most wonderful good afternoon. Let's go. Yes, let's do it. Good afternoon. That's the right spirit. Most wonderful good afternoon. Most wonderful good afternoon. Right, let's get going. Let's do things. Good afternoon. Have a lovely afternoon. Thank you. Thank you very much. Oh, your usual space has been usurped.
I know. It's not right, is it?
If I'm straight on, maybe I'll understand better.
Oh, today will be absolutely easy.
No.
What do you mean no?
Correlation.
Seen this?
Yeah, correlation coefficients.
I don't know what any of that means.
Oh,
I know
but Alex, that is why you are here. Because if you knew it, I would say, what the F are you doing here? Right?
I'm still mildly ill though.
Well, can I please ask you very politely to keep your germs to yourself?
Trying.
I mean, sharing is not caring in this case. I don't care about you.
Just get sold off.
Okay, most wonderful good afternoon, ladies and jelly beans. Friday afternoon. For those of you who sort of like to spot patterns, you probably noticed that you haven't got an email from me, the Friday, the obligatory Friday prayer email. Don't worry, I haven't forgotten about you. It will come later on, but I want to see how far we get today before I make any announcements. Okay? So don't stress. You'll get it, I promise. Whether you want it or not, I don't care. Right. So today I want to do a little bit of perhaps new stuff. Why? Just simply because somebody molting here. No, it's not me. I don't have that much hair.
That's very
Because this stuff is quite important for bioscientists, and we will encounter that quite frequently. And a lot of people struggle with that, and they do all sorts of weird and wonderful things with correlations. I say weird and wonderful things because I want to avoid the phrase doing bad things. There are a lot of very, very bad people out there that are doing very, very bad things to data. I call them data abuser. And I will give examples of people who do these things because I don't want you to become one. I think this is a criminal offense, and people should go to jail when they do horrible things to data. But we will discuss that. So, usually, correlations, we are all absolutely 100% familiar with correlations because we do correlations all the time. Sounds terribly complicated, but it's not. And I think every single language on this planet has a sort of a phrase, the more I do something, the more whatever. So the more, the more. And that is actually a correlation. It is a typical example of a correlation. So the more I practice calculations, the more I become confident in doing things. Right? That's a typical correlation. It consists of two variables. And that's why we are dealing with correlations of bivariate, means two variable, data. So, for example, the more I earn, the more I can spend. It's a nice correlation. And in this case, the correlation, the first more and the second more, the more I earn, the more I spend, they both go in the same direction. More money, more spending. So, more earning, more spending. Earning goes up, spending goes up. Both go in the same direction. Less earning, less spending. Also go in the same direction. If we have a correlation like that, so earning and spending are correlated, and both go in the same direction, this is called a positive correlation. So positive correlation, if they go in the same direction. Of course, you can have also a negative correlation. So, for example, the more time I spend on social media, the less time I spend on revising. So, more social media, less revision. And in this case, the two variables go in different direction, more and less. When we have that case, then this is called a negative correlation. Pretty and simple definition. So positive, negative. Can we have no correlation? Well, pretty much. A lot of things are not correlated with each other. So the more time I spend on social media, it doesn't actually matter. It doesn't have any influence on the weather. So me spending time on social media and the weather, there's no correlation in it. So we can have anything from positive to 0 to negative correlation. Now, we said we are dealing with two different variables which are dependent, or sort of, which are correlated with each other. And just for sort of clarity, when we do plots, we are talking about these two variables, and there is a particular convention how we plot these data. And I think I mentioned that already when we did the assess practical. We deal with the independent variable. This is actually the variable that we either manipulate or that we can easily observe. So in a way, it's in the hand of the researchers, this independent variable. And depending on this independent variable, we have a dependent variable. So the independent variable determines how big the dependent variable will be. Sometimes people, especially in social sciences, use the term predictor and outcome. Or independent variable x, the dependent variable is y. And that is exactly how we are going to plot things. The things that we observe, that we have under control as a scientist, we plot on the x-axis, that's the independent variable. No. Let's try to get this straight. That's our x, that's the independent variable. And that is what we can control. And on the y-axis, we plot our dependent variable. And that's the outcome. Very often you will see it's the other way around, that people do it the other way around. Every time I look at something like that, where it's the wrong way around, it's sort of a little bit of my soul dies. it goes like, "Ugh." Haven't you learned anything from Clapper's statistics? Apparently not. And what we can do now is we can look at data, whatever these data are, and we can say, right, at data point 1 here of my x, I do a measurement and I get y here, this particular y value. And another point x, that's 2, value 2, we get that data point, and so on and so forth. And we get, for example, something like that. And that's a nice correlation. Is it positive or negative? It's positive. Why? It's going up. Yeah, it's going up. But in a way, what you can say is the more x I have, the more y I get. Yeah, and therefore the line would go up, and therefore it is a positive correlation. You have done that GCSE? Yeah, something like that? Brilliant. Now, obviously, it's not a straight line, is it? And what people very often do is they say, right, I do a line of, loud? Best fit, right. How do you do a line of best fit? So in this case, you would go, oh, right. I just try to sort of get it done that it is sort of something like that. Yeah? Looks pretty good as a best fit line. I'm really proud of myself. What is your criterion for best fit in terms of data? What would you say? Ideally, it would be sort of, you know, half of the data above the line, half of the data below the line. True? Yeah, that's sort of how we do it. So we can do best fit lines, but of course it's not terribly precise in a way. If you think about it, I could have done it slightly differently. How does a computer actually do it? Well, computers do it differently. And for that, let's go back a little bit. Let's just simply say we have some data, some x data, some y data. And to illustrate that, here's a little table. I hope you can see that. And can you see that? All right? Yeah? So here are 4 data points. And these data points actually are actual data of mice. So it's not a terribly exciting experiment. It is a correlation between the length of a mouse and the weight of a mouse. And the question is there a correlation there? Now, as you can see, the data are a little bit all over the place. But what we can do is we can actually say, right, conceptually, we have two sets of data. So we have our x, that's the length. Can't remember. I just make up some number, 12, 10, 14, and 9, or something like that. Yeah? So this is one set of data. And from this set of data, of course, we can do our beloved statistics. Alex? Beloved statistics? No way? Oh, yeah. What we can do, for example, is we can calculate a mean for that. Yeah? That's pretty simple. We know it's a sample because the world does not exist just out of four meses. We've got more. And we can calculate a mean. How do we actually do the mean? Well, we just add them all together and divide by the number of counts. That's pretty straightforward. So what we could do is we put the data that we have the x values. No, let's not do it that way. And we can do that, the same thing, we can do that for the weight. With data, we can also measure the mean for the weight. And we get nice means. We can also do standard deviations or variances for that. So we can calculate a standard deviation and variance for weight and length of the data. And what we can do is, actually, we can now, again, we can plot the data. Like I've done before. Something like that. And we can say, right, I just look at the mean of the data like that. That would be my mean line for the weight. Well, it's just simply the mean of the data. How do we calculate the variance for these data? Well, it's very easy, because we said for the variance, what we do is we just simply measure how far away are the individual, oops, that was the wrong one. We measure how far each data point is away from the mean. Then we take the square of it and divide by, well, depending on whether we have a sample or a population, we divide either by n or by n minus 1. That was our variance. So this would be described as the variance of the mean line. So let's keep that in mind. But in our case, what we have is, obviously we have not a nice horizontal line. We have a line that goes up. Ugh! Bum! What can we do with that? Well, actually we can calculate a variance again. We just sort of, in our mind, we tilt that line, again, do the variances, the difference of our data point to this line. Yeah? Can you imagine that? You just tilt it, or you just, tell you what, you just keep your head that way, then it is level, yeah, and you've got it. Don't tilt it too much, because with some people, brain might drop out. So it's, yeah. Or you get a stiff neck. But the principle is exactly the same. You can calculate a variance. This would be actually the variance of the line of best fit. I can hear you saying, Master, or Sir. That's all nice, but how do I know this line of best fit? This is exactly what we want to find, isn't it? Well, actually, computers can do that, because what they can do is they can say what we want is this variance to the line of best fit. We want that to be as small as possible. Because if this variance is very small, that means the difference between our data point and a line is very small. So small variance of the line of best fit indicates that we found a good line. And that is actually what most computer programs do. They optimize it. They go through a lot of different sort of starting points for this line and see, can I fit the line to the data so that this variance from the line is as small as possible. And that's an optimization program. There are also some mathematical equations how you can do that, but they are a little bit hairy, so I'm not molesting you with these equations. And that is basically what a computer program does. But what it is just nothing else but just simply a linear line. Just a line, linear, straight line. How do we express a straight line? You know, it's always, what is it? Y equals mx plus c. Y is our dependent variable, x is our independent variable. Now we want to indicate, however, that this, what we have here, is actually sort of a line of best fit. And people have a slightly different way of writing that, the equation for a line of best fit. I noticed last week on the group chat there was a discussion about why everybody has to use this constant k. Why the heck is there always a k in something? You will be absolutely delighted to hear this time it's not a k. The line of best fit usually is expressed as y equals I love that. I love that. I love what's coming next. What would you call it, this M now? Right? What was it? Yeah. It's called beta sub 1 x plus beta naught or sub 0. This is just convention. From what I'm concerned, feel free to call it, instead of beta sub 1 or M, call it Paul. I don't care. Yeah, or Alan, or cornflake, as long as you are consistent. But this indicates that we are dealing with a line of best fit. And, of course, it's a line of best fit. But if you look at it, it's not correct yet, because our outcome is not always on the line, exactly on the line. For example, this point here is away from the line. Is away from the line. So we need to add an additional component to our formulaic line, which we don't have in the normal straight line. And this additional component is an error component. And the error in this case, because we've got Greek symbols, and I know that this is confusing, is lowercase e, Greek. It does not mean extinction coefficient in this case. It means error. That's the error component. Are you still with me? Sort of? Yeah, I know it's Friday afternoon. But so far we haven't done really any maths, right? So it's you are safe. So that's the line of best fit. And I show you later on how you can actually find this line of best fit if you are using Excel or Google Sheets. It's not very difficult. It's just a single command that you have to give for that. But before we do that, we need to talk a little bit about how we measure actually how good the fit is. So here is a line with data. Which line has a better fit? Left or right? In which line, in which side are the data better correlated with each other? Right. It's on the right. Absolutely, you are right. Here we have much better correlation. By the way, positive or negative correlation? positive correlation, absolutely, because the line goes up. Much better correlation. But how do we express the correlation? How can we do that? Well, there is sort of an equation which you don't have to learn. And this correlation was developed by a guy called Pearson. It's not the one from the exam board, but it's sort of a little bit related to. And he came up with a sort of a way to calculate how good a correlation is by coming up with the idea of, hey, let's look at the variances. Variance of the mean minus the variance of line of best fit divided by the variance of the mean again. This was sort of, for Pearson, a way to figure out how good is the correlation. Now we know that a variance is always sort of the square of the standard deviation, right? So the variances are all squares, and that's why we have this R square value, because it follows on from the variances. So, let's quickly check. Variance. Can a variance be negative? Yes or yes? No? Variance can't be negative. So we have only positive numbers in it. Variance can't be negative because we square everything, add that up and divide by something. So variance is always positive. So we've got positive numbers. And in this case, the variance from the line of best fit is always smaller than the variance of the mean. So the whole expression is always a positive number. We can't even go further and say, what is the range of that number? If the variance of the line of best fit, if it is 0, that means there is no deviation of the data from our best fit line. Every single point is 100% on that line. This part here would be 0. And R squared would be 1. Absolutely, because variance of mean divided by variance of mean gives 1. Bam. So if the data are totally on the same line, R squared equals 1. Now here comes the trick. Because this R squared, we can actually interpret that. R squared tells us how much of our outcome data can be explained by the predictor, by the x. So r squared, how much of the outcome is explained by predictor variable. In our case, where they are perfectly lined up, 100% of the data, 1. Now, what happens if the variance of the line of best fit is basically the same as the variance of the mean? What do we get? What would it look like? The variance from the mean and it's difficult to draw that. So basically the data are all over the place. In this case, variance of mean equals variance of best fit. And in our equation here, what would we get? What would we get for the numerator? Loud? 0. And 0 divided by anything is always 0. So in this case, our r squared would be 0. That means none of the variables none of the outcomes that we observe can be explained by the predictor. Predictor is just, doesn't tell us anything. Number of butterflies in the garden correlated to cheese consumption in Maine. There's no correlation there. R squared would be 0. Nothing can be explained. So that's the meaning of R squared. Side note, I will not ask you ever to have to calculate an R squared value. Although I will show you how you do that in Excel, because that's quite useful. Now, what is this little r thing that you originally saw? Well, r is basically nothing else but square root of r squared. But there is an additional piece of information in little r. We said capital R, r squared, can be anything between 0 and 1. R also indicates whether it's a positive or negative correlation. That means little r can be between positive 1, that means perfect positive correlation, and negative 1. That means a perfect negative correlation. What does a perfect negative correlation look like? it would look like something like that. The line goes down, it's a negative correlation, and everything is on the same, on the line of best fit. That's the negative perfect correlation. And it can be anything in between. Now, sort of a convention is that people say, if R is larger than, let's put that somewhere else. If R is larger than 0.8, it is a strong positive correlation, or if R is smaller than negative 0.8, the correlation is strong. If R is larger than 0.9, it's a very strong correlation. If no, that should be the other way around, shouldn't it? If R is between 0.5 and 0.8, it's sort of, well, yeah. I suppose there's a correlation there. Yeah, well, so medium correlation. Anything between 0.5 and 0.2 is a weak correlation. If R is around 0, there is no correlation. So if we are really honest, we are looking for strong or very strong correlations. That's predominantly the interesting bit. So we are looking for an R of at least 0.8. Because if you think about it, 0.8, if R 0.8, how much of our data can be explained by the x value? What is R squared in this case? (0.8 squared. What is 0.8 squared? (0.64). Only 64% of our data can be really explained by the independent variable. So, 36%, we can't really explain with that. That makes sense? So what I want you to really understand is that we are looking for R larger than 0.8 or smaller than negative 0.8 if we are speaking about a strong correlation. Now obviously we need to quickly talk about something that I have seen more often than I really wanted in the assessed practical. You had some data. And it looked like that. Does that look familiar to some? Yeah? So we have a fairly good correlation, a line of best fit, but we have a sort of bum data. What's that? What's it called? Outlier. So if you say to me this is an outlier, I would ask you, what kind of outlier is it? Outliers can be with respect to the independent data, or it can be with respect to the dependent data. Is it an outlier with respect to the independent data? Is it out of the x-axis data? Or is it out of the y-axis data? You can very easily answer this question by just moving the data point. An outlier is defined as a data point that does not fit the majority of the other data. Now, what you can do is, in order to identify an outlier, and there are some methods, I might write something about that and email you that. But in terms of an outlier, to identify whether it's an X or a Y outlier, what you do is you just simply move it, or mentally move it, and the direction you have to move it so that it fits with the other data, and the direction you have to move it tells you whether it's an X or Y outlier. So which direction do you have to move it? Sideways or, so horizontally or vertically? Vertically. So that would be, if you move it just simply down, that indicates it's a dependent variable or Y outlier. What would be an X outlier? An X outlier would be, say, a data point over here. Which way do I have to move it to bring it back to its mates? Would probably go in that direction. So that's a typical X outlier. Sometimes we do that deliberately. If we want to measure a wider spread of things, then we have X outliers. Let's have another one. Do we have any outliers? No outliers? Now that's interesting, because this point here is certainly not with their mates. It's certainly not with all the other Y or with all the other X. So it would be an outlier. It would be an XY outlier. It's both. But actually, it's not that far away from our line of best fit, is it? But it is away from our line of best fit. So we can have an XY outlier This here would be another one. It's also an XY outlier. And these XY outliers, they can be actually quite important. Why? Because, think about it, if you were to decide on a line of best fit, you would say, right, I could either totally ignore this XY outlier, or I can take them seriously. And now, in this case, I would draw a line of best fit probably like that. Now, these XY outliers actually have a massive impact, have a massive influence on the slope of your line of best fit. If I didn't have this one here, I would probably go for this one here. And because of these XY outliers that have this influence on the slope, these outliers are actually called influential points. An influential point, as it says on the tin, is an outlier that, in a way, has a massive impact on how you would draw your line of best fit. Does it make sense? Now you would probably argue with me, really, when are we going to deal with influential outliers? We haven't done that in A-level. Have you done them in A-level? No? Influential outliers? We haven't done them in A-level. We haven't done them in GCSE. So really, surely, they can't be that important. I had to break you the news, but have you, those of you who have done biology A-level, I think probably everybody has done biology A-level, yeah? Have you done A-level? Yeah? Have you done double reciprocal plots in A-level? Where you look at, you've done Michaelis-Menten plots, where you measure the velocity of a reaction versus the substrate constant. Have you done those? Yeah? Some of you have done those? Yeah? And you discovered that these plots are crap, as we will discuss next term. And therefore, you came up with a different kind of plot. 1 over V versus 1 over S. Have you done those? No? Damn it. Really, you haven't done them? Ugh. That's disgusting. I thought everybody does them at A-level. Oh, we are going to have fun next term when we do enzymes. Because that's one of the famous plots, which is also crap. And this is actually a plot where you are constantly dealing with influential points. And that's why this plot is crap. Right? So, watch out for it. Be excited. I will also show you another plot for the enzymes next term, where we have yet another violation. I told you on the These are the dependent. And on the x-axis we have the independent. The next term, I show you a plot where you have a mixture of dependent and independent on the x-axis. And I tell you what, if that doesn't get you into a sweat, nothing will. So I'm looking forward to that. But coming back to these outliers and influential points, I really want you to distinguish between outliers, be able to distinguish between outliers and influential points. Outlier, you might say, right, something went wrong. I may or may not ignore that. Influential points have a massive impact on how you set up your line. Okay? Make sense? I suggest we have a 7-minute break, and then I show you how you can abuse data, and also how you can do really nice analysis with spreadsheets. 7 minutes break. Wasn't a lot of terribly new and exciting stuff, was it?
No, it was okay.
Was okay, good.
Don't know how you do it, but you've covered a year's worth of A-level statistics in about 3 hours.
Is that good or bad?
It's made more sense now than it did at A-level.
Really?
Yeah. Yes! Because before you just plug in numbers into formulas and you don't really know what you're doing, but it comes out with the right answer.
Well, but it would be nice to understand
Yeah.
how you do it.
Yeah.
Have you done Pearson R?
Yeah.
Yeah. Good. So shouldn't be a problem.
Yeah.
Have you done it in Excel?
No. No, it's always just done on the Casio.
Oh yeah. Let's do it. Does it make sense?
Yeah.
Yeah. Not terribly exciting. The
No,
whole.
like it's kind of as you go through it, like it's kind of all base knowledge that I've heard before, but it's good to go through it because it's been a while.
Okay, yeah, is what I thought. Have you done actually how you do these things in Excel, in spreadsheets? Good. Good.
Just found my exam data sheet. Given that, plug the numbers in, you get the right answer. I've no idea what I'm doing and what it means, but I get the right answer.
You know, nobody in their right mind would ask you to do something like that.
Well, they
but
do.
you get the... Yeah, but I show you how you can very easily get these things.
Yeah, S1 is very useful. I only did AS maths, so I know how to do all this stuff, but I don't know what it means and how I can apply that to like real world stuff. I can plug numbers into equations.
But then, you know, if I had a monkey and I would train the monkey,
Yeah.
yeah, but what you really want to know is why, how,
Yeah.
yeah. So, how do I get, for example, how do I get the slope of the best fit?
Yeah.
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 How and what does this R square actually mean?
Yeah.
Well, now you know.
Yeah.
It tells you how much you can explain.
Yeah.
Okay, can we reconvene then? Because I want to show you actually how you in real life can get these R-square values, the slope, and also the intercept of such a correlation. So what I've got here is, again, some mouse data. You can tell I've got a sort of affinity for Mises. I like them, they are cute. And what I want to do now is I want to see whether there is a correlation. So the thing that you always should do is look at the data, especially when you think there is a correlation. Look at the data and plot them. And in this case, the way you would plot it is you always use, in Excel at least, and in other spreadsheet programs, you always use a function called scatterplot. Never, ever, under any circumstances, use line plots. Line plots just simply plot an ascending series of numbers on the x-axis, which has usually nothing to do with your independent variable. So always go for scatterplot. I'll show you how to do that. So you just simply highlight your data, go to Insert, Charts, and go for scatterplot, right? Of course, your plot should then have axis titles, which in Excel you just simply can add with this one here, chart title, axis title. I don't bother because, you see these are our data points here. We have the weight as the dependent and the length of the mouse as the independent variable. How do we get a line of best fit? In Excel, it's incredibly simple. You just simply go to one of the data points and right mouse click. You open a new menu, and second from the bottom is Add Trend Line. And this gives you a line of best fit. Now what you want to do is you actually want to make sure that you have linear, it always comes up with linear anyway, and everything else you don't need to worry about. However, if you scroll down a little bit, you will find that you can tick boxes. You can display the equation on the chart, and also you can display the R-square value. So in this case, you get the values for the slope. So it's about 3 for the slope. That's this one here. That's the slope. And that's the intercept, 13.02. So it gives you these important data for the line of best fit. It also gives you the R-square value. So do we have a very strong, weak correlation here? What do you think? Is it strong or very strong? Strong. Why is it strong? Be careful. Why is it strong? Sorry? Is it less than 0.9? Yep. R. Yes, thank you. So 0.82. What's the square root of 0.82? What is it? 0.905. So this would be considered a very strong correlation. Yeah? Always read the label. Okay? Now, if for one reason you can't do that, can't plot anything, and in Google Sheets it's a pain to plot, something like that, and it won't give you that easily the slope, the intercept, and the R square. There are formula. In Excel, as you know, each formula, each expression starts with an equal sign. Equal. Now, if you want to get the correlation coefficient, you just simply type correl. It comes up with something predefined, and it asks you for the first array, that's this one here, separated by a comma, second array, and we close the bracket, and it gives you R, the correlation coefficient that you just calculated, right? So that's the command for the correlation coefficient. You can do the same thing, so that would be R. You can do the same thing for the slope, for the gradient, and what you need to do is you enter equals slope, and it comes up with something. Now here it depends on the order how you input it. It asks you for the y values first. So that's the y, separated by a comma, and then it wants the x values. Close. The slope gives you roughly 3. Right? And if you want the intercept, for the intercept, all you need to do is equals, guess what you have to put in? Huh? Yep. Intercept. And again, it asks you first the y values separated by a comma, x values, close bracket, and you've got your equation. Simples. So we have our equation for the line of best fit. Slope, intercept, and an R square value, and an R value. Now, if you think about it for a moment, these data here, our Mises, it tells us a correlation between length and weight. Would we expect this to be true, not just for these 4 mice that we've checked? We probably would expect that to be true. So in a way, what we have here is only a sample of many more mice we could have tested. Or we could have picked 4 other mice. Yeah? So what we get here with these slope and intercept is actually only a sample. And we said every sample also has a sort of a confidence interval. A confidence interval in where we say, right, the true population value for the slope is in this confidence interval. Yeah? How on earth do we find this confidence interval for the slope or an intercept? I could show you the equations. You wouldn't be happy. But Excel can do the trick if you ask very nicely. How do you find the confidence interval? Well, you have to install something in Excel, and I show you how you do that. It is called Data Analysis Tool Pack. Have you installed that on your computer? No? So what you do is you go to Data on the ribbon and you check whether you've got the Analysis Tool Pack installed. It's nothing here. It should be here. There's nothing there. So let's install it. Go to File and Options. Go to Add-ins. Excel add-in at the bottom, Go. Comes up with this one. And here it's the first one, Analysis Tool Pack. Check that. Click OK. Cool, we've got our data analysis tool pack here. In this data analysis tool pack, click on it, and it comes up with a menu where you can select a lot of things. For example, you can select descriptive statistics. Should you ever be asked about descriptive statistics, it's there. In this case, you want a regression. Regression is nothing else but a posh word for best fit line. Click on it. And it comes up with some questions. So, first of all, it asks you for the input for the Y range. Just simply keep the left mouse button clicked, select it. Input X range. Select, click. Actually, let me I select the labels as well. Okay, now I've got the labels selected. I want a confidence interval, 95%. And let's say I want a new worksheet. Press OK. Wow, I get a lot of analysis here. I get my R-square value here. I get my intercept here. I get my slope here. And I get for the intercept, I get a confidence interval down here. Lower 95% confidence interval and upper. So I found the slope in this case is 3. But it tells me here with the confidence interval, the slope can be anywhere between negative 1 and positive 7. So the slope can go like that. The slope, can it be flat? Yeah, that would be 0. And it can even go down. So basically, in this case, everything is possible. It means I do have a strong correlation. I have a very strong correlation, but actually the data are not enough to decide whether the population slope would go up, stay flat, or even go down. Slightly different for the intercept. Well, the intercept, it could be anywhere on the y-axis. It could be in a negative range, it could be 0, it could be positive range. So in this case, we have a huge variety possible. So we can't make a conclusive statement whether length and weight are positively correlated or not correlated or even negative correlated. Could very well be that it is negative. So although we have a strong correlation, we can't make a firm conclusion what it looks like. So why on earth do I tell you that? Why on earth do I tell you that? Usually people would say, right, we have our data. R squared is 0.8 something. R is positive. It's a positive correlation, and it's a very strong one. Hey, fantastic! We have a strong positive correlation between length of the mouse and weight. If you start digging a little bit and then ask, what is the confidence interval? You start wondering, actually, is there a positive correlation? And the confidence interval for the slope says, no, there isn't. It could be a positive correlation. It could be no correlation. It could be a negative correlation. That is what I want you to get from that. When ordinary mortals do the analysis, they are happy. Yes, we've got a slope. Yes, we've got an intercept. Brilliant. You are victims of Clapper. Yeah? You are victims of Clapper. You know better. And I expect better from you. So whenever you do a correlation, I want you to think, wait a moment. He told us about this confidence interval. Let's see whether this is really the case. And I showed you how you do that. If it was too quick, there are lots of YouTube videos how you find a confidence interval of a slope. Because I don't want you to be data abuser. And there are, as I said, there are bad people out there. For example, people who just simply do lots of extrapolation. You have a set of data, y and x. Something like that. And you say, actually, what I want to know is what would be my y value over here at this x value. And what these people then do in cold blood is they just say, all right, we just extend our line. Oh, look, we've got this point here. Extrapolation with data. Incredibly popular, incredibly dangerous. Why? Let me show you. And I hope I don't offend anyone. Do we have anyone from the beautiful state of Mississippi in the US? No? Brilliant. So I can, say all sorts of things. Now this is actually adult obesity rate of adults in Mississippi. And in 1990, there was a 15% obesity rate in adults. In 2018, it went up to 40%. So 40% of the adults in Mississippi are fat. And some people then say, right, in the year 2110, and you see it's a really nice straight line. So we just simply extrapolate that, and in the year 2110, 103% of the people in Mississippi will be obese. That means every single adult will be obese, plus 3%. Wait a moment. Where do these 3% come from? Is there people who, well, but then by default they are living in Mississippi. So where is this? Maybe they are the, actually I don't know. But what you get is you can't extrapolate, right? It's not allowed. Under no circumstances you can extrapolate, especially when you're dealing with percentages. That is data protection. Don't abuse data. Another thing is, and that's quite interesting, correlation is not the same as causation. Just because there is a correlation between two data sets, it does not mean that one causes the other one. Just to give you an example, sale of ice cream and the incidence of skin cancer. What do you think? Is there a correlation? Sale of ice cream and skin cancer. Alex goes, no? Yes. Actually, it goes like that. There is a strong correlation between skin cancer and sale of ice cream. So, if you want to avoid skin cancer, don't eat ice cream. Bollocks, hey? Or, only people with skin cancer eat lots of ice cream. Doesn't make sense either, does it? So we have a correlation, but there is no causation. Or is there? Why do we see a correlation like that? Now that is where science comes in. Why do we see a correlation?
Because the days when you're going to have higher sales of ice cream is going to be nicer weather, so people are going to be outside and therefore more likely to get the
So we have, you're absolutely right, we have a variable that affects both. We have a variable that affects sale of ice cream, and we have at the same time the same variable affects skin cancer. And in this case, it's probably not so much the temperature, it is temperature plus UV exposure. Yeah? But this is not a variable that we have explicitly stated. These variables are called lurking variables. Or confounding variables. But I like the word lurking variable much better. They are lurking in the background. They are there, but nobody sees them. They are really disgusting. They are hanging around. They are there. You have been probably told something about a lurking variable without really knowing it. When you started in September, did somebody show you a graph between attendance and grades? There is a very strong correlation between attendance and attainment and the marks that you get. The more you attend, the better your grades. True? Well, this is what people tell you. That's why we said we do attendance monitoring, because if we force the students to come, they will learn more. What could be the lurking variable for that? Sorry? Amount of revision. Yeah, would amount of revision actually influence the attendance? I have a suspicion, but I haven't done the research. What could be affecting both attendance and grades? Work ethos, motivation. Motivation could affect both. If I am highly motivated, I really want to go to the lecture. And at the same time, I really will do the practice questions, I will do the reading around. That's the lurking variable. Most people in this university don't get it. They still insist on attendance monitoring because that will increase the grades. Bollocks. It's not going to increase the grades. There's something totally different in it. So, be careful of lurking variables. And always think about these lurking variables when you see correlations. And there are some really, really exciting and interesting correlations out there. For example, in Sweden, in the 1950s, they did an analysis and they measured over the years the number of storks and plotted it versus the number of babies. And lo and behold, guess what? They saw a strong positive correlation. Conclusion: babies are brought by the stork. We knew it. This is what we have been told. So forget all the contraceptive crap, you know. If you don't want to get pregnant, don't let the stork near you. Yeah? Is there a lurking variable? Well, there could be a lurking variable in terms of, well, people feel more settled, have more babies. They look after the environment. Storks feel happier, breed more. Could be a lurking variable. I just want to show you a few more interesting correlations. And actually there's a website with what is called spurious correlations. So, for example, the number of people who drowned by falling into a pool and the films Nicolas Cage appeared in. You see, it's almost perfect correlation. If it goes up, if one goes up, the other one goes up. If the one goes down, the other one goes down. Now, of course, you could say the lurking variable is the quality of Nicolas Cage's acting. So the more film he appears, the more people perhaps want to drown themselves. Per capita cheese consumption and the number of people who died becoming tangled in their bed sheets. Well, even the ancient Romans knew that cheese actually gives you bad dreams. So there could be a lurking variable. Divorce rate in Maine and per capita consumption of margarine. A perfect negative correlation. So maybe it is, if you don't want to give your partner the margarine for breakfast, they give you the marching orders. Sorry, you didn't give me the margarine, so I want a divorce. Age of Miss America and murders by steam, hot vapors, and hot objects. I mean, if you see something like that, a correlation in a scientific paper, you would say, wow, of course, yeah, totally believe it. So whenever you look at correlations, think about the babies and the storks or Miss America. Ask yourself, does that make sense? Or if you say, could there be a lurking variable? And never ever just simply calculate a single point estimator like slope or intercept. Always do the whole hog, the confidence interval. And also ask yourself, what do the data actually mean? So if we go back to the mice, where is it? We said for the mice we had the intercept of 13, so length and weight, 13, and a slope like that. So it would look like that. Actually, let me draw it like that. So that is what our graph showed us, yeah? Now what do these things actually tell us? Well, in this case, it only tells us sort of an equation. If we extrapolate that, the intercept in this case, does it have a physical meaning? Well, it would mean that a mouse who has no length still has a weight. 13 grams actually. So no mouse weighs 13 grams. Oh, that's a bit weird. Doesn't make sense, right? So in this case, intercept and the slope don't have a physical meaning. But if you think about it, we had examples where these things had actually a physical meaning. Remember that example? Natural logarithm of a versus time. What kind of kinetics was that we plotted and it gave us a straight line? What was it? Loud? It was right. So that was, you're absolutely right, it's the first order. Right? Now in this case, the intercept has a meaning. The intercept here actually means natural logarithm of A, our initial concentration of A. Yeah? What was the gradient? If you remember that? It was the constant K. Yeah, we've got it back. It was the constant K. So what we can do in this case is we can calculate our confidence interval for K. So we can say K plus minus this margin of error that we calculated. Can we actually calculate a confidence interval for our initial concentration A? If you look at that. Can we? The answer is no, we can't. Bugger it. Or not that easy. We can calculate a confidence interval for, but the intercept is actually ln A. So we can calculate a confidence interval for ln A, for the natural logarithm of A, initial, plus minus MO, our margin of error. But we can't do that because we have only ln. And converting that into what I just crossed out is a total pig. So just be aware of that. Think about the babies, think about the storks, and have a wonderful weekend.